Hello guys, welcome to my channel Algorithm Avenue. In this video, we'll be discussing about multi-layer perceptron. Okay, before diving into the definition of multi-layer perceptron, let's take a quick recap on how the single perceptron fails in classifying the non-linear data. Okay, this is the non-linear data that we have taken for example. Now, when we feed this data points to the single layer perceptron, what it does is it tries to draw an linear line to classify this data. Okay, but this linear line doesn't divide this data points into two different classes. Okay, we have one class is blue, another class is black, but when you see that our single layer perceptron is not at all dividing into two different classes. Okay, this is a case of non-linear data. Okay, to overcome this kind of problems in classifying the nonlinear data, what scientists have done is they introduce multi-layer perceptrons. Okay, first now let's define a multi-layer perceptron. Okay, a multi-layer perceptron is a class of feed-forward artificial neural network. Okay, what feed forward means is when you take a simple neural network, let's take a perceptron for an example. Okay, this is an perceptron. These two are the input data and this is our output data. Okay, in our perceptron, how our data flows is, as this is our input. Okay, this is our input x1, let's say, and this is our input x2. Okay, how our data flows in a perceptron, I have already explained you in in our previous videos that these two inputs first pass through this connection. Okay, pass through this connection, and some mathematical operation is done in this perceptron, and your output data is calculated. Okay, output data y hat is calculated. You see that the how the propagation is, it is in the forward direction. Okay, the inputs from here are flowing till here. Okay, this is called feed forward. Okay, you are feeding your input data in the forward direction, so it is called feed forward artificial neural network. Why it is called artificial neural network? Our brain neurons are biological neural networks, but the neural networks that we are creating to solve our basic problems is artificial neural network. We are taking some artificial neurons. We are taking some artificial neurons to classify, means to solve our basic problems. Okay, a multi-layer perceptron is a class of feed forward artificial neural network. Okay, that consists of multiple layers of nodes. Okay, in perceptron, what we have seen is we used to have a single perceptron. Okay, nodes are nothing but perceptrons. In early 80s 90s, we call these nodes as perceptrons, but in the early times the perceptrons are called as nodes. Okay, that consists of multiple layer of nodes. Okay, now how multiple layer of nodes look like is, let's say, let me rub this. Okay, this is some basic artificial neural network. Okay, this is some basic artificial neural network. This from here my input goes, these are my layers, and these three are my layers. Okay, that consists of multiple layers. This is one layer. Okay, this is one layer, this is one layer, this is one layer. Okay, multiple layers of nodes, and means each layer consists of multiple nodes. Okay, we have multiple layers, and each layer consists of multiple nodes. Okay, that consists of multiple layer of nodes where each node is connected to every node in the adjacent layers. Okay, now let's understand this. Now this node, take the connection of this node. This node is connected with this node in the adjacent layer. In the adjacent layer, this node is connected with this node, and this node is also connected with this node. Now take this node. This node is connected with this node in the adjacent layer, and this node in the adjacent layer. Okay, now when it comes to this case, this node is connected to this node in the adjacent layer, and this node is connected with this node in the adjacent layer. Okay, similarly for both these nodes as well. Okay, a multi-layer perceptron is a class of feed forward artificial neural network that consists of multiple layers. Okay, each multiple layer consists of multiple nodes and is connected to each node is connected to each and every node in the adjacent layers. This is called multi-layer perceptron. In a single layer perceptron, we have only single perceptron, means this only this single perceptron. But in multi-layer perceptron, we have multiple perceptrons. Okay, multiple perceptrons and multiple layers. Okay, now, in this segment, let's understand the structure of a multi-layer perceptron. From that definition, we have created a multi-layer perceptron. This is just an example. You may have a multi-layer perceptron with any number of nodes and any number of layers. Okay, this is just an example that I'm showing over here. Okay, let's just take a simple problem statement for describing this structure of multi-layer perceptron. Okay, x1 is your input feature. Now, okay, this x1, x2, x3, x4, these four are your input features. Okay, x1 is one of the input feature, x2 is one input feature, x3 is one input feature, x4 is one input feature, and for this corresponding features, this y is your true output. Okay, this we have four input features and one output column. Okay, for this four input features, we have one corresponding output column. Okay, now we represent the basically what we do is we represent the input features with a dot. Okay, this x1, if you have five input features, there will be another dot and connecting to this these nodes. Okay, as we have four input features, we have taken four inputs. Okay, x1 is one input feature, x2 is one input feature, x3 is one input feature, x4 is one input feature. Okay, in that definition, what we have seen is, and multi-layer perceptron is a feed forward artificial neural network. Means our input data must flow in a forward direction. Means this input data must be given to these corresponding nodes, from these corresponding nodes must be given to these corresponding nodes, and from these nodes to these nodes. Okay, now we are feeding our input data x1, x2, x3, x4, these four features to our multi-layer perceptron. These four features are fed to our multi-layer perceptron. Okay, these are represented by x1, x2, x3, x4. Okay, next what we do is we given connection. We given corresponding means, as we have to feed each input to each and every node. Okay, we have connection to this node and this node and this node as well. Okay, from these x1 data must be fed to this node, this node and this node. Similarly, x2 data must be fed to this node, this node and this node. Similarly, in the case of x3 and x4. Okay, first x1 is fed to this, x1 is fed to this, x1 is fed to this, x2 is fed to this, x2 is fed to this, x2 is fed to this. Okay, now from this layer, okay, this is layer number 0, this is layer number 1, this is layer number 2, and this is layer number 3. Okay, this is layer number 0. This is where the input comes to the multi-layer perceptron, that is layer number 0, and this is layer number 1, this is layer number 2, and this is layer number 3. Okay, after the input data has reached here, some mathematical calculations are done in corresponding to each node, and from here the input data goes here. Okay, as we have talked that multi-layer perceptron is a feed forward artificial neural network. From here our input data has gone here. Okay, from here again it will go here and output is calculated. Okay, now in each and every node corresponding mathematical calculations are done. Okay, now this is our input layer, from where the input is coming to the neural network, that is called input layer. Okay, from input layer to it is coming to this layer, right? From input layer it is coming to this layer, so it is called first hidden layer. Okay, from input layer the inputs are coming to this layer, so this layer is called our first hidden layer. Okay, from here the outputs are coming becoming as inputs to this layer, so it is called second hidden layer. Okay, now from here the outputs of these two nodes, okay, the outputs from this layer are coming to this layer. Okay, so it is called an output layer. Where the output is calculated, that is called output layer. Where the calculations are taking place, that is called hidden layers. And where the input is coming to the multi-layer perceptron, that is called input layer. Okay, this is input layer, these two are our hidden layers, and this is our output layer. Okay, now if you have n number of features, you'll have n number of inputs over here. Okay, now why we have taken this two layer two hidden layer is our corresponding to our problem statement. These two hidden layers are sufficient. Okay, if you have more complex like n number of, you have many number of inputs and you have more complex problem statement to solve, then you have multiple hidden layers with multiple nodes. Okay, in this case we have only 3 nodes, but you may have 5 nodes, you may have 10 nodes. From in here you have only 2 nodes, you may have 10 nodes, you may have 20 nodes. Okay, it completely depends on the problem statement. Okay, in this way hidden layer is altered. Hidden layer can be altered based on the complexity of the problem statement. The input layer is altered based on the number of inputs. Okay, the output layer, okay, how can we decide the number of nodes in the output layer is based on the number of output columns. If this is y output, and if you have another output y1, then there will be another output node, and here y1 hat is calculated. Okay, in this way the output layer nodes are altered. Okay, if you have multi-class classification, then you'll have multiple nodes in the output layer. Okay, now let's see the notation of each and every connection, means each and every parameter in a multi-layer perceptron. First let's understand why these notations are important. Okay, these notations are important because they help in understanding the backpropagation algorithm. Backpropagation algorithm is well understood when we have notation to each and every weight or each and every bias. Okay, and before notation, we need to have total number of parameters in an multi-layer perceptron. Okay, first we need to know how many parameters are there in a multi-layer perceptron. Then each parameter must be denoted with some corresponding weight denotion or bias. Okay, now let's see how to calculate the number of parameters in a multi-layer perceptron. Okay, now we have four input columns. We have four input features, right? We have four input columns, and here we have three nodes in a hidden layer. Okay, in this hidden layer we have three nodes. In this layer we have four input features. Okay, now 4 into 3 is equal to 12. This 12 is nothing but number of weights, means number of weights between this layer and this layer 0 and layer 1. We have 12 weights. Okay, as we know that each as we know that each connection has an corresponding weight. Okay, generally in a singular perceptron also, this connection has an one weight and this connection has a weight. Similarly in a multi-layer perceptron also, from here to here we have one connection, right? This has some weight and this connection has some weight. Okay, from here to here we have some weight, from here to here we have some weight, from here to here we have some weight. Okay, the number of connections determine the total number of weights. But in case of bias, each node has a single bias, means this node has an one bias, this node has one bias, this node has one bias. Okay, each node has a single bias, but each and every connection from between the nodes has a corresponding weight. So when we have four input features and corresponding to adjacent layer 3 nodes, we have 12 weights. Okay, from here to here we'll have one weight, from here to here, from here to here. Okay, similarly for all the four input columns. Okay, we have 12 weights, and from between the layer 0 and layer 1, how many bias we have? B11, B12, B13. So 12 plus 4, 16. Okay, we have 16 parameters between the layer 0 and layer 1. Okay, now let's see for between the layer 1 and layer 2. Between layer 1 and layer 2, we have 3 nodes over here and 2 nodes over here, means total 3 into 2, 6 weights. That is 3 into 2 is equal to 6 weights. Now total number of bias is B21, B22. Okay, 2 bias, so 6 plus 2 is equal to 8. We have total 8 parameters between layer 1 and layer 2. Okay, now let's see for layer 3, layer 2 and layer 3. Okay, between layer 2 and layer 3 we have two connections, means we have two nodes and here we have one node, 2 into 1, so it comes to 2, and we have bias over here for this node, so total 2 plus 1, that is 3. Now total number of parameters is 16 plus 8 plus 3, which comes to be 27. We have total 27 parameters. Okay, in this multi-layer perceptron we have 27 parameters. Okay, now let's see how to denote bias, weight and output of each and every node. Okay, first let's talk about bias, how to denote an bias. Okay, generally the general form of denoting a bias is bij. I denotes layer number, I denotes layer number, J denotes node position in that layer, in the layer. Okay, the bias is represented by general form, that is Bij, where I denotes the layer number and J denotes the node position in that layer. Okay, now for this let's take a few examples to understand. Now for this node, the what is the layer number? Layer 1. Okay, this node is in the first layer and the position of this node is first, so it is denoted by B11. Okay, now let's see for this node, it is in the first layer, and it is in the second position, so it is denoted by B12. Now when it comes to this node, it is in the first layer and it is in the third position, so it is B13. Now let's see for this node, that is output last layer, that is the last layer, only we have single node. Okay, this is in the second layer, 1 2 3, sorry, this is in the third layer and first position. Okay, this is B31. Okay, this is in the third layer and is in the first position, so it is called B, so it is denoted by B31. Okay, this is how we denote and bias. Now let's see how to denote and weight. Generally weights are denoted by WKIJ. Okay, this is the general form of denoting and weight. Okay, now what K represents is layer number. Here in case of weights, K represents layer number, I represents. Okay, now let's understand how the representation looks with an example. Okay, first in case of this, let's take an example, this. Okay, for this connection we have weight, right? Okay, now how this weight is denoted is, first here k value is 1, that is in the first layer, k value is 1, means this connection corresponds to this layer, right? This connection corresponds to this layer, so it is represent k value is 1. Okay, from where the input is coming to this node, from the first position, that is from the first input feature, so it is I value is 1. From where this input is going to where this input is going to this node, where this node is, it is in the first position, so it is represented by W11. Okay, now let's see for this. Okay, from here to here, this connection. Now let's see for this connection. Okay, now for this connection, it is in the layer number 1. Okay, it is in the this connection is in the layer number 1, so k value is 1. Now from where the input is coming to, from second feature. Okay, from second feature the input is coming to second node, so it is represented by W122, suffix 22. Okay, now let's see for this node and this connection. Now let's see for this connection. Okay, now what is the layer number? It is in the third layer, so W3, k value is 3. From where the input is coming to this node, from it is coming from this node, right? Where this node is, it is in the first position. In second layer, it is in the first position. Okay, in case of denoting the weights, we need to calculate only the position of the nodes in that layer. Okay, so it is in the first position and it is coming to the first position, so 1 1, it is represented by 1 1. Okay, when it comes to this connection, when it comes to this connection, the layer number is 3. Okay, the layer number is 3. From where? From second node. So I value is 2. From where to where? To first position. Okay, from second position node to first position node. So 2 1, it is taken as 2 1. Okay, the whole denotation is 3 2 1. Okay, now let's take a final example. Let's say this. Okay, let's calculate for this, let's denote for this connection. W, in which layer it is located? W2 in the second layer. From here these connections are belonging to layer 1, these connections are belonging to layer 2. Okay, this is layer 2. from third position to, it is going to second position. Okay, from this third position to, it is going to second position. So 3 2. In this way weights are denoted. Now let's see how we denote the outputs of each node. Okay, for this node we have one output. For this node we have two outputs. Okay, these connections determine the number of outputs for this corresponding node. Okay, we have two outputs. For this node we have two outputs. For this node we have two outputs. For this node we have one output. For this node we have one output. For this node we have one output. Okay, now how the outputs of the each node is denoted is OIJ. OIJ. It is similar to the bias. How we denote the bias? Similarly, we denote the output of each node as well. Okay, for this node. Okay, for this node, the outputs are O11. Okay, why O11? That is, this is a ij, right? This is ij, right? What I denotes? Layer number. It is in the first layer. J denotes the position of the node. Okay, it is in the first, this is in the first layer and in the first position. So it is Oij. So it is called O11. No, for this node O12, it is in the first layer and second position. Now for this node, it is in the second layer. It is in the second layer. Okay, it is in the second layer and it is in the second layer and it is in the first position. Now for the output of this node, it is in the it is in the sorry, it is in the third layer and it is in the first position. So it is O31. Okay, it is O31. I have made a small mistake in calculating the total number of parameters. Actually, when it corresponds to this between these two layers, we have total. This 12 is correct. This 12 is correct. We have 12 weights, and we have only 3 bias over here. Okay, not 4, only 3. So it comes to 15, and this number comes to 26. Okay, we have 26 trainable parameters. Okay, 26 trainable parameters in this multi-layer perceptron, and this O31 corresponds to the output. This O31 corresponds to the output of this multi-layer perceptron. Okay, the output of each node is same. Okay, in this connection the output is O11, and in this connection output is O11. Similarly, in this connection the output is O12, and this connection output is O12. Means the, if we have multiple outputs to an node, if we have multiple outputs, then outputs of then all those outputs are similar. Outputs are same. Okay, if you have multiple outputs for an each layer, for an each node, then all those outputs are same. Okay, this is O12 and this is O12, this both are same. But where this gets altered is, when this goes from this output, it goes to here and becomes input to this node. From this node, from this output goes over here and becomes input to this node. Okay, this is one separate node, this is one separate node. So here the output gets altered. Okay, but generally the output of each node is same. Okay, if you have multiple outputs, all the outputs of that node are same. Okay, now in determining the total number of layers in a multi-layer perceptron, we don't consider an input layer. This layer is not considered. In determining total number of layers in a multi-layer perceptron, we don't consider this input layer. Okay, only this hidden layer and this output layer becomes the total number of layers in an multi-layer perceptron. Okay, in this case we have three layers. So it is three layered perceptron. Sorry, this is three layered multi-layer perceptron. Okay. Now, when we have now in this case, okay, I hope it's visible. In this case, we have this is one hidden layer, this is one hidden layer, and this is one hidden layer. So three hidden layers and one output layer. So it is four layered perceptron. It is a four layer perceptron. It is a three layered perceptron. And in determining the number of layers in an multi-layer perceptron, we don't consider an input layer. Okay, we don't consider an input layer. We only consider an hidden layers plus one output layer. Okay, hidden layers plus one output layer in determining the number of layers in an multi-layer perceptron. Okay, now when it comes to activation functions, we have and single activation function means this whole layer has only same activation function, but this node means for each node separately we don't have an activation function. The activation function is common to the whole layer. Activation function is common to an whole layer. We don't have activation functions for single nodes in a layer. Okay, now this node, this whole layer may have an activation function or may not have an activation function. Okay, this whole layer this whole layer may have an activation function or may not have an activation function. Okay, this layer may have an activation function or may not have an activation function, but for single node we don't have an activation function. In common to all these nodes we have single activation function. In common to all these nodes we have single activation function. In common to this node we have single activation function. For a layer we have only one activation function, because at the times of back propagation, okay, at the times of back propagation it becomes difficult for the multi-layer perceptron to calculate, means recalculate the weights. Okay, gradient calculation becomes difficult. Okay, when we have single activation function for an each layers, then it becomes easy for the backpropagation algorithm to determine the gradients. Okay, this is the whole intuition of structure of multi-layer perceptron. Okay, hope you like this video. If you like the video, please like, share and subscribe. Thank you.